So as always, I have a video going over this quite slowly, but during the Zoom, I'm going to show you a few examples. That way you can get it down. If you have questions, either in class or virtual, by all means, you're more than welcome to interrupt me at any time. That way you can get your question answered quicker, and I can understand probably better what you're talking about. So let's take a look then with the visualizer at that sheet and a few problems. Oh. Hopefully that is clear for you. Let me see if I can clear this up at all on my end. You guys can do that, right? If you follow along with me on the sheet, then you'll know exactly what I'm talking about. If you're having difficulty, if this is fuzzy for you. So if we take a look, C6H6, every combustion reaction, what do we add? What does every combustion reaction require if you're burning something? Oxygen is required. Why is this not written correctly? It is diatomic, so we need O2. Very good. What were you going to say? Yeah, no, it's diatomic. You were close, right? Bi-di. So if we take a look, does anybody know what these reactions always produce? Yes. H2O and CO2 is perfect. Carbon dioxide and water, right? This is why burning fossil fuels is talked about for climate change, because of that CO2 being a powerful greenhouse gas. And we use carbon hydrogen compounds like octane and things like this in our cars, diesel fuel, in our factories. Coal is a combustion reaction that produces carbon dioxide and water. Used all over. We've been using it for quite some time. So that's why that is always talked about as being detrimental. Now, the last thing, all of these are going to be gases because of the amount of heat. This H2O is not in a liquid form. It's in a gaseous state. In the wintertime, when a car is like pulling off the line of a stoplight, have you ever looked at their tailpipe and see that liquid pour out? Like whenever they start to go on a cold, cold day, that's actually that water vapor that has condensed from the car sitting there. That's not like unspent fuel. That's just water vapor that's condensed. So if we take a look, we've got to match up each side. So the first thing we want to do is match these C's up. I have 6 here. What do I need to put in front of CO2 then? 6. I do my hydrogens next. 6H. So I need 2 times X equals 6. 3. And here is the trickiest part. I've got 12 plus 3, which is 15 O's on this side. I only have O2 on this side. So what can I multiply by 2 to get 15? Louder? 7.5. And here is the universal rule for writing balanced equations, though. You cannot have half a molecule. Doesn't work. So I have to somehow keep all of these ratios equal and in whole numbers. So how can I keep all of these the same ratio, but have a whole number for the 7.5? You have a brother? Yep. Do you like cookies? You like cookies? All right, so for every 1 cookie your brother gets, if you get 1.5, how can you maintain that ratio without breaking cookies in half? You could have 3, and then he would get. If you get 1.5 for every 1 he gets, and you get 3, how many does he get? He would get 2. So all we've got to do, what he did there with those numbers, was he multiplied both of them by 2. So if we multiply every single number here by 2, the ratio maintains, right? Instead of a 1 to 7.5, it will be a 2 to 15 to 12 to 6. And let's just check it to make sure. 2 times 6 is 12 C's. 2 times 6 is 6 times 2 H's. 15 times 2. We've not seen the likes of a number this big, but 15 times 2 is 30. Well, 12 times 2 is 24, plus 6 is 30. So we maintained it. We maintained it. Let's try the next one. The next one's probably the hardest one on the page. Again, you could sit here and write this for all of them. Right? It's the same reaction. Combustion reactions are the same. You can just forward my name on that pass. I don't think anybody's going to check it. Just make it a scribble line. Make sure you put a time. Who's your teacher you're going to? Who's your study hall teacher? How many kids are in the cafeteria study hall right now? Is it 100? Maybe. It's not like almost every year. Then they have to spray those down, and then for fourth period. Wow. I didn't even know. Sorry about that. All right, so let's go ahead. And put these in here. Have a good day. I'll see you. I'll see you on Zoom tomorrow, right? So 1C, 1C. 3 plus 1 is 4 H's. So I need 2 times 1 to get 4. That gives me 2 plus 2 oxygens. That's a total of 4 oxygens. Here I have 1 oxygen, so I have to subtract that 1. What's 4 minus 1? 3. Good, right? We throw the easy ones in there too sometimes. So how can I make 2 into 3? Well, Mr. Cookie, what do I do? 1 and no, multiplication wise. So how do I make 1 into, or 2 into 3? What can I multiply 2 by to get 3? We just did it with your cookies. 1.5. 1.5. 1.5 times 2 is 3. Again, I cannot have half a molecule. I cannot have half a molecule. So what do I have to do? To maintain the ratio, I multiply everything by 2. So that is 2. That is 3. That is 2. And that is 4. Let's check it. 2 C's, 2 C's. 6 plus 2 is 8 H's. 2 plus 6 is 8 oxygens. 2 times 2 is 4. Plus 4 is 8. Let's do one more. I'm going to do this one that looks crazy down here. C7H16. That's a chemical called heptane. Octane has 8 carbons. Heptane has 7 carbons. So not all of these require that crazy method that I'm doing. We can have 7 carbons here, and we can have 16 hydrogens here. 7 times 2 is 14, plus 8 is 22. So what am I going to put in front of the oxygen here? 11, good. So there's no funkiness there. There's no trickery or anything there. So it's not always like, oh, I've got to do that weird half thing. That's not always the case. Sometimes it's the case. Again, keep in mind that the combustion reactions, the hard thing is not figuring out the products. It's always the same. In this class, we always talk about complete combustion. There are no other products besides these 2. The trick about combustion reactions is balancing it. Excuse me. So don't forget, the primary assignment for today is to make sure you have that laboratory done, right? So if you don't have that laboratory done, please make sure you go through and get this laboratory and write-up done. And then do a few more practice combustion problems. By the end of this period, I hope to put the review up. If it's not there by the end of this period, it'll be up there before the end of the day for sure. That's what I got. I'm going to show the guys here a few demonstrations. I'm going to use the Zoom camera to do that. So you're more than welcome to stick around and watch these demonstrations. Otherwise, you're more than welcome to get out of here and go on it and get work done. But we're going to do some combustion reactions. Give me 1 second to switch the camera, and then I'll set it up. All right, so make sure you're on presentation mode so that this is the big one. Again, how do I make this the big one? I think that's up to you to make this the big one. All right. So right here we have what's called the gas valves in the classroom. And students always ask me, what happens if the flame comes out of here? Like if this gets igniting somehow. People have seen way too often in movies where a flame comes in and then like reaches something and then explodes the entire thing. But this is a gas jet. So if this ignites, the flame just comes out of it. It doesn't go inside of there, right? Why can't the flame shoot in there and ignite? What's not in there? Oxygen, right? So oxygen is required for that flame to burn. It can't go inside of there. Now, what if somebody did put oxygen in there, and oxygen and the gas were coming out? Well, then it's possible. Let's create that scenario. We're going to make a small bomb. So here I've got a coffee can. And what I'm going to do is I'm going to put this gas in here. I've got a little hole at the bottom. Okay, we need to do some boxers. So I put some gas in there. And now I'm going to ignite that gas on top as it comes out of that hole, as it diffuses is the term. We haven't seen this yet, have we? We have. Oh, well, you guys stop me then. Never mind, you guys saw this one yesterday. This is the boring one. I'm just gonna sit here, this right here, because you didn't remind me. No, I'm kidding. That's the boring one. I got a different one for you then. I forgot that I showed this class. So let's try this one out. Here I've got a big container. This is a like a water tank thing. And here I've got what we call methanol. Methanol is a, what do you call it? It is an organic compound, carbon and hydrogen. And I'm going to pour about 50 milliliters in there. 20 milliliters in there, in a 50 milliliter beaker. I'm going to dump this into here, and I'm going to mix it all around. All right, do like a little methane dance. I'm going to turn the lights out. Get that methanol all around inside of there. And then we're going to ignite it again. Set some matches right here. I don't want to have my hand near this one. Ready? 3, 2, 1. Oh, you got it there and lost it. 3, 2, 1. You can see the reaction continues to occur, and it stops. Why do you think that reaction stopped? Because it was pulsating like a heart. Justin, do you know?
I don't think so.
Well, let's just play a quick game with it then. Anybody in here got an idea of why it stopped? Did it run out of oxygen or did it run out of the other stuff? Let's check it. Let's check it. So what you guys are telling me is that whenever I pour this out, whatever this is right here, that right there is not flammable. Let's just check. Give me 1 second, sir. Oh, maybe it's not. These are the worst matches ever. Is it flammable? Yeah, it is. Yeah, it's flammable. So that means that it did not run out of the flammable stuff. It ran out of what?
The combustion caused like formation of CO2 that didn't put out the flame.
That's a possibility. But the other thing is, if we tried that reaction again, there's not enough oxygen in here to make it work. And CO2 is heavier, isn't it? Now, if you see right here, and I don't know how well this is on the camera at home, but right there you can see like this little redness. I don't know if you can see that or not, unfortunately. But that redness is from another chemical. That redness is from lithium. If you want red fireworks, you use a substance called lithium to make that red coloring. That's kind of cool. Let's see if we can mix that around a little bit more. I want to make sure the people at home can see that. So I need the fire from the methanol, and the lithium is what makes it turn red. So let's try this. Hopefully at home you'll be able to see this a little bit better. There we go. So I don't know if the actual, well, these are the matches. But I don't know if the actual camera has the ability to pick up the red tint that we're seeing here. Can you guys see that red? Yeah, that's the color of lithium. Pretty cool. Hopefully the smoke detector doesn't go off, right? But there we go. That's all I've got for you guys. Thank you very much. And those of you that are coming tomorrow, I'll try to think of a cool demonstration that we can do, and we'll let them see it virtually. Have a great day. And you guys have the rest of the period to work through that as well. I got to sign off of this unless you have questions real quick, because I am recording it. Do any of you have questions? All right, I'm going to go ahead and end it then so I can put that, whatever you call it, up on the Zoom.